Okay, hey everybody. So as you can probably tell, I'm not here on Thursday. So I decided to record a video where we go through a couple of examples of linear systems. Okay. So our first example here, we want to solve this linear system. We have x prime of t equals 3x of t plus 4y of t. Y prime of t equals negative x of t minus y of t. And we have the initial values x of 0 equals negative 2 and y of 0 equals 2. So step one, we take the Laplace transform, right? And so I know that a couple of people were struggling on how to take this Laplace transform. All I'm using here is that the Laplace transform of x of t. I'm calling that big X of s, okay? The Laplace transform of y of t, right? That's going to be big Y of s. And then now we have to use our properties here that if I take the Laplace transform of the derivative, I get s times x of s minus little x of 0, and the Laplace transform of y prime of t, same thing. We get s y of s minus y of 0, okay? But now, of course, we can go ahead and plug in what our x of 0 is. It was just negative 2. Right? So minus a negative 2 becomes plus 2. And then same thing here, right? We can go ahead and plug in what our y of 0 was, which was positive 2. So we get minus 2 here. And so that's how I get the left-hand side of these equations. Right on the right-hand side, I think that's pretty self-explanatory. Okay. So that's step one. Step two is now we solve for x of s and y of s, okay? So we have to first get x of s, all the x of s terms on the left-hand side, all the y of s terms on the left-hand side here, okay? So in our first equation here, we're going to subtract 3x of s on both sides. So we'll have an s times x of s minus a 3 times x of s. And if I factor out the x of s, I just have s minus 3 times x of s, okay? This plus 2 that's on the left-hand side, I'm going to subtract that over. So now we have a 4y of s left over and then minus 2. Okay. Same thing for this equation, right? I need to add y of s to both sides. So I'll get an s plus 1 y of s then. And I'll add 2 to both sides, and I'll have negative x of s plus 2. Okay. Now that I have it in that form, I need to substitute one equation into the other equation. And I usually start with the second equation here. So ignore the red bubbles and the blue bubbles here for just a second. I have s plus 1 times y of s equals negative x of s plus 2. If I want to substitute the first equation into the second equation, then it would be great if instead of x of s, I had s minus 3 times x of s. Okay. So I'm going to multiply both sides of my second equation by s minus 3. And you can see I've done that in red over here. So now every single term has an s minus 3 in it. So we have s minus 3 times s plus 1 y of s equals negative s minus 3 x of s plus 2 times s minus 3, right? Where I've taken the second equation and every term gets multiplied by s minus 3. Okay. Now that I've done that, well, s minus 3 times x of s in the red circle here, right? That's exactly what this is, and that's equal to 4y of s minus 2. So I can replace that whole term there with 4y of s minus 2, not forgetting that there's still this minus sign on the outside, okay? Everywhere else, I just use a little bit of algebra, right? I FOIL this out, right? I distribute this over here. Okay. And then now, right, I can go ahead and distribute this minus sign. And when I do that, I get a plus 2 over here. So minus 6 plus 2 is minus 4. Okay. So I have s squared minus 2s minus 3 times big Y of s equals negative 4 y of s plus 2s minus 4. And then now, again, I want to get all of my y of s terms together. So I'll add 4y of s to both sides. And now I have s squared minus 2s plus 1 times big Y of s equals 2s minus 4. Okay. Now I can factor s squared minus 2s plus 1 into s minus 1 quantity squared, okay? Which is great, because I'm going to need to divide by this factor later to solve for big Y of s, okay? So then on the right-hand side over here, right, where I have this s over here, right, that's going to be in the numerator of one of my fractions then after I divide by s minus 1 squared. And it would be great if we could cancel that off. So I rewrote s as s minus 1 plus 1. Right? I think everybody can agree that that's equal to s, right? But the reason I chose s minus 1 plus 1 rather than s minus 2 plus 2 or s minus 3 plus 3 is that if I leave it as s minus 1 like this, that'll cancel off with one of my factors of s minus 1 on the left-hand side when I divide by it, okay? So now I'll distribute my 2. So I have 2 times s minus 1, and then plus 2, right? So then minus 4 plus 2 is minus 2. So I got that there. Okay, now I'm ready to divide by s minus 1 squared, and I get that y of s is equal to 2 divided by s minus 1. So there's that one factor of s minus 1 canceling off of this. So 2 over s minus 1 minus 2 over s minus 1 squared. Okay. So now, right? Well, now that I have y of s, I could do like I did in class, and I could plug in what y of s is over here, and I could solve for x of s that way, right? But it's actually going to turn out to be a lot better for us if I just use the same trick that I did over here, right? I want to plug the second equation into the first equation, right? So I need to take my first equation and I need to multiply everything by s plus 1 so that I can make that substitution there. So I'm going to take my first equation and I'm going to multiply it by s plus 1, which you can see I've done in blue here. So that's exactly the same as this first equation, but now you see that every term gets multiplied by s plus 1. Okay. All right. So now I'll simplify that, right? This s plus 1 times big Y of s, and it's the same thing as the thing circled in blue over here, so that becomes negative x of s plus 2. So that's how I get this over here. I distribute this to get negative 2s minus 2. I distribute this to get s squared minus 3s minus 3. Okay. And then now I'll go ahead and distribute this 4, so I get negative 4x of s plus 8, but then 8 minus 2 is 6. Okay. And then now I'll combine my x of s terms by adding 4x of s to both sides. So I still get this s squared minus 2s plus 1 times big X of s. That's nice. Okay, and it's equal to negative 2s plus 6. I'll play the same trick here where I'll factor this as s minus 1 squared, and then I'll rewrite this s as s minus 1 plus 1, right? I'll distribute the negative 2, right? So I get a minus 2 over here plus 6 becomes plus 4. Okay. Now I'll divide by s minus 1 squared, and I get that x of s is equal to negative 2 over s minus 1 plus 4 over s minus 1 squared. So here I've collected my x of s and my y of s together over here, and that's the end of step 2. Okay. Now, step 3, I'll take the inverse Laplace transform of both of these, and I'll get that x of t equals negative 2 e to the t plus 4t e to the t. And so here I'm using my Laplace inverse table, where the Laplace inverse of, and if it's just a constant over s minus a constant, right? That Laplace inverse is c times e to the at. Okay. If, on the other hand, we have something like this, like c over s minus a squared, okay? Well, for that one, I need to use my shifting property, okay? So I can go ahead and factor my c out, no problem, right? And then the Laplace inverse of s minus a squared, right? Well, that's just going to be equal to e to the at times the Laplace inverse of, well, instead of an s minus a in there, I'm just going to have an s, okay? And then now the Laplace inverse of 1 over s squared is just t. So I get c e to the at times t. And so that's how I get that the Laplace inverse of 4 over s minus 1 squared is just 4 times t e to the t, right? Because my a is equal to 1, right? And this constant c is just 4. Okay. I'm going to do the same thing over here, right? So the Laplace inverse of 2 over s minus 1 will just be 2 e to the t, right? The Laplace inverse of 2 over s minus 1 squared, well, my c is equal to 2, right? My a is equal to 1, so I have 2t e to the t, okay? And so that's how I get my answer there, okay? And so notice that I put my final answer here with these curly brace x of t and y of t together, and then I just boxed it off so it's easy to find, okay? Now let's try this one. Okay. So this is another one. We're going to solve it basically the same way. Okay. So here's my system, right? Here are my initial values. Step 1, take the Laplace transform. Okay. So it's s x of s minus x of 0. So that's how I get the minus 6 there. Right. Down below, it's s y of s minus y of 0. So that's how I get the 8 there. Okay. All right. And then on the right-hand side, that's self-explanatory. Now for my step 2, remember I need to solve for big X of s and big Y of s. So the first thing I do is I group all of my X of s terms on the left-hand side for my first equation. On my second equation, I group all of my Y of s terms on the left-hand side. Okay, so that's going to leave me with s x of s minus 4, right? Sorry, s minus 4 times big X of s. And that's going to be equal to negative 2 Y of s plus 6 after I add that 6 over. Okay. Just down below, something very similar. We get s minus 4, big Y of s is equal to 2x of s plus 8. Okay. Now, I'm going to substitute my first equation into my second equation, which means I need an s minus 4 times big X of s. So notice here in red, I'm multiplying all three of my terms by s minus 4 in my second equation there. Okay, and then I simplify after that. I FOIL this out. I get s squared minus 8s plus 16 times big Y of s is equal to 2 times, now you see where I've plugged in this thing in the red. Okay, so that's negative 2y of s plus 6, and I need to distribute that 2. Right here, I've already distributed the 8 to get 8s minus 32. Okay, so then after distributing this, we get s squared minus 8s plus 16 times big Y of s is equal to negative 4 big Y of s plus 8s minus 20. Now I'll add my 4y of s to both sides, and I get this. S squared minus 8s plus 20 times big Y of s is equal to 8s minus 20. Now, I can't factor that. This is actually an irreducible polynomial, which means that it has no x-intercepts, right? Which means that you can't factor it as linear terms over the real numbers, okay? So this is going to be a quadratic term where I'm going to have to complete the square in order to finish this problem. So completing the square works like this, basically. So if I have like, let's say I have an ax squared plus bx plus c, okay, and I want to complete the square on that, then I'm going to start off by factoring an a out of everything, okay? Just its first two terms, really, okay? And I'll leave the plus c on the outside, okay? And then now what I'm going to do is, in order to factor this, I'm going to add and subtract b over 2a quantity squared. Okay, all on the inside of the parentheses over here. Okay, and when I do that, here's what I'm going to wind up with. I have an a over here still on the outside, right? This first terms over here, these first three terms, they factor very nicely as a perfect square. This just becomes x plus b over 2a, quantity squared. And then everything else, well, I'll distribute this a to this term, right? So we're going to get a b squared over 4a squared times a. So then what's going to be left over here? Well, I'll go ahead and FOIL it out here. So b squared over 4a squared, okay, and then plus c. And so this just turns into a times x plus b over 2a, quantity squared. I'll distribute this a over here, so we're going to get a plus c minus b squared over 4a. Okay, and so that's how you complete the square always, right? So now in this case, right, where we're factoring this polynomial over here, right, our a is equal to 1, okay? So basically, I just need to add and subtract b over 2 quantity squared. So 8 over 2 quantity squared, sorry, a over 2, 8 over 2 is 4, so if I square it, I get 16, right? So I need to basically borrow a 16 from this 20, okay? Yeah, it's the same thing as adding 16 and subtracting 16, right? Because 20 minus 16 is just 4. Okay, so now that I've borrowed that 16, this thing factors very nicely as s minus 4 quantity squared, and I still have this 4 left over. Okay, now I can divide by that, and I get that y of s is equal to 8s over this quantity minus 20 over this quantity. Okay, all right. And although that looks horrible, right, because I've completed the square and everything, that's actually something that is easily recognizable from the Laplace inverse table, right? So I'll go over that in a second. Okay. But now I have to do the same thing for x of s, right? So I'm going to take my second equation, I'm going to plug it into my first equation, which means that I need an s minus 4 times big Y of s here. So I'm going to multiply my first equation by s minus 4 everywhere. Okay, so that's what you see in blue over here. Now that I have that, right, I'll go ahead and do exactly the same steps as before, right? I'll FOIL everything out, basically. I'll make my replacement s minus 4 big Y of s, right, which is going to be equal to 2x of s plus 8, right? So that's what you see over here. Okay, so after combining everything together, right, we get this. Okay, but now I need to add my 4x of s to both sides of the equation. So we'll get this again, right, which we already know how to complete the square on that now. So I'm just going to go ahead and do that. Okay, and that's going to be equal to 6x minus 40. Okay, now I'll divide by this, and I get that x of s is 6s over this minus 40 over this. So then I've collected my terms here. Big X of s is equal to this, big Y of s is equal to this, and I'm ready for step 3, where I do the inverse Laplace transform. Okay. So how to take the inverse Laplace transform of something like this, right? Oh, I made a slight mistake here, actually, right? So I need to go ahead and fix that. So maybe you'll see it in action right here. Get rid of this. Okay. So the mistake I made here is that we know what the Laplace inverse of something like this looks like. If it has an s minus beta over s minus alpha squared plus beta squared. Okay. So the Laplace inverse of something like this is actually not too bad. Oh, sorry, I said s minus beta. I meant s minus alpha upstairs. Is not too bad, right? It's basically instead of an s, you have an s minus alpha everywhere, so it's shifted by alpha units. So this is going to be the same thing as e to the alpha t times the Laplace inverse of, well, instead of s minus alpha, now we'll replace it with s. So it's s over s squared plus beta squared. Okay, and that's an easy Laplace inverse there. This is just going to be e to the alpha t times cosine of beta t. Okay, so I want to take the Laplace inverse of this function over here, 6s over s minus 4 squared plus 4, but it's not quite ready yet. So I'm going to transform this a little bit. So before I do step 3 here, I'm going to do a little bit of algebra here. Okay, so my big X of s is equal to 6 times, and I'm going to write this as s minus 2 plus 2. Okay, right? Oh, sorry, I said s minus 2 plus 2. I meant s minus 4 plus 4. There we go. Okay, all over s minus 4 quantity squared plus 4. Right, over here we still have minus 40 over s minus 4 squared plus 4. We'll talk about that one in a second. My big Y of s, I'm going to do basically the same thing, right? So I'm going to say this is at 8 times s minus 4 plus 4, okay? All over s minus 4 squared plus 4, right? Minus 20 over s minus 4 squared plus 4. Now, the reason I've chosen to do that, right, is because since I have an s minus 4 downstairs over here being squared, I need an s minus 4 upstairs in order to use this property. Okay, so now I have to clean this up yet again. So my x of s is going to be equal to, well, I'll split this up into two fractions basically. So I'll have a 6 times s minus 4 over my s minus 4 squared plus 4. Okay, and then I get plus 24 over this, but then I'll combine that with my minus 40 over this, right? So this is going to turn into a minus 16 over s minus 4 squared plus 4, right? Because I have a 24 minus a 40. Okay, my big Y of s, I'm going to do the same thing. Okay, so this is going to be an 8 times s minus 4 over s minus 4 squared plus 4. And then now I have a 32 minus a 20. So it's going to be a plus a 12 over s minus 4 quantity squared plus 4. Okay. Okay. And then now I'm ready for step 3. Okay. So my step 3, I'm going to do the inverse Laplace now. Transform. Okay. And so now I'm going to use this property here. We're taking the inverse Laplace of s minus alpha over s minus alpha squared plus beta squared. Okay, so this is going to turn into my first term here is going to be 6, right? I'll go ahead and factor that out. I have my e to the 4t, and then I'm going to have cosine of 2t, right? My beta squared is 4, so my beta is 2. Okay. All right, so that's that first term there. And now I need to subtract off this 16 over s minus 4 squared plus 4. Okay, so that requires yet another inverse Laplace property here. So here I'm going to have a, let's say we have a constant, any constant you want, divided by s minus 4 squared plus, oh, sorry, not s minus 4, s minus alpha squared plus beta squared. Okay. So in this case, right, I could go ahead and start off by factoring the constant out, right? And then now the Laplace inverse, right, since this is an s minus alpha squared, I'm going to get an e to the alpha t from that. And now this becomes the Laplace inverse of just 1 over s squared plus beta squared. Okay. All right, but now that I have that, now that I've pulled that e to the alpha t out, right, the Laplace inverse of 1 over s squared plus beta squared, right? Well, that's just going to be equal to 1 over beta times sine of beta t. So then I'm going to write this as c over beta e to the alpha t times sine of beta t. Okay. Basically, if this had a beta upstairs, that would be the Laplace transform of sine of beta t. But since it doesn't have a beta, I need to divide by beta to make sure there's one there. Okay. All right, so then this next term over here, right? I had a 16, right? But I need to divide by my beta, which is 2. So then I'm going to get minus 8 e to the 4t sine of 2t. Okay. My y of t, I'm going to do the same thing. So I have 8 e to the 4t cosine of 2t. Okay. And then now I'll get plus 12 over 2 is 6 e to the 4t sine of 2t. Okay. And there we have it. Okay, hopefully that helps. If you have questions on this, right, well, first I advise you to watch the video over again, a few times, pausing when necessary to make sure that my algebra is correct and everything, and to look at our table of Laplace transforms that is posted in Folio, right, and look at those properties, the ones that I'm using, and see that I'm using them correctly. Okay. And then if you still have questions after that, right, and then again, watch it multiple times, right? But if you still have questions after that, email me, right? Even with a timestamp in the video so I can look at it and kind of explain what I do in a particular step. Okay.